Hello and welcome to this webinar. My name is Iqbal Singh Josan and I'm going to present this webinar today on antenna engineering part 2B of 2. Actually, we covered part 2A of 2 last Saturday and the leftover is we are covering today. And those of you who have missed the previous webinars in this series, including part 1 of 2, you can visit our website usprotect.com and go to the webinars page and you can always view our recording of the previous webinars. Okay, so let's begin now with today's webinar. Well, these are the topics we are going to cover today. We are going to talk about base station, indoor and mobile handset antennas. And we'll talk about how antenna tilt can be used to improve the performance of base station antennas. And then the interesting topic of MIMO, which stands for multiple input and multiple output. We'll discuss this in a little more detail. We'll see how we can realize the benefits from this new technology and what are the different techniques used to realize those benefits, including antenna diversity, beamforming techniques, and space division multiplexing, or in short, it's called SDM2. Then we'll reflect on the applications of MIMO in Wi-Fi, WiMAX, and LTE, and see how all these newest 4G wireless broadband standards, they have adopted MIMO technology. Then we'll just have a glimpse of the future of MIMO, where this technology is heading us. Okay, so with that said, now this is a slide about these cellular base station antennas. Well, this is a familiar picture all of you must have seen, the cell tower. At the top of the cell tower, you have antennas looking like this. Now, these antennas, they can be either omnidirectional, that means they transmit equally in all directions, or they could be directional. In most of the urban and suburban areas, you usually have the directional antennas because the user density is very high and you need to focus all your energy on the desired user population. And because of the high density of users, directional antennas give better performance and better coverage and add to the system capacity, as we have seen in the previous webinar. Now, omnidirectional, they have a limited application, but they do find application in rural or countryside areas where the users are very far apart. So the directional antennas may not work there. So you just have to transmit in all directions and to cover all the users. And typically, the gains will be between 5 dBi to 24 dBi. If you recall, dBi means decibel isotropic, with reference to an isotropic antenna. These could be mentioned in terms of dBd also, but here we are saying 5 dBi to 24 dBi. And most commonly, they are linear polarized. The polarization is linear, vertical polarization. If you see, the rods are vertical, so rods means the electrical field, the E field vector is in vertical direction. And they could be, it's rarely somebody deploys multiple polarizations, but you could have them dual polarized too. That means plus minus 45 degree polarized to support polarization diversity and derive gains from that. But most commonly, the vertical polarization serves well in most of the situations. Then, of course, the radiation from these antennas is in broadside. That means it's at 90 degrees or perpendicular to the structure, as you see in the picture. So this is a typical cellular base station antenna. Well, the wireless LAN antennas have this, they look different, as most of you must be having a Wi-Fi at your home or business or wherever you work. So they have a different look. There are outdoor wireless LAN antennas with a higher gain of 20 to 24 dBi, which are used to cover long, narrow regions or links between buildings. These usually you don't see because they're at the top of the building or on the side of the building. And they are used mostly in enterprise wireless LAN networks. Then you could have flat panel antennas, which can be used outdoor as well as indoor. Typical gain is little lower gain because the distance covered is much smaller. And of course, this can be used to cover large regions where the user density is located in a very small area. Then you have indoor omni. This is the most common consumer wireless LAN antenna. If you have seen or you own a wireless router, you must have seen these type of antennas installed on the device. They are usually low gain because it covers a very small area, 100 feet, maybe 200 feet, or even less than that. And they are very commonly used in wireless access points and routers. Okay, with that said, now handset antennas. So handset antennas are a different story altogether because, handsets, they present unique challenges. You have to often have a trade-off between the design performance you expect from the antenna in a handset and its placement. Handset is full of many other peripherals too. You have the wireless circuitry, you have the screen and the keyboard, and all this. All this is packed in a very small space. So where do you find space for the antenna? So there are some unique designs have come up. One is the most common is the planar inverted F antenna, or PIFA design. This design, you fabricate this antenna on the PCB, on a sort of PCB. In the picture, you see a PIFA element for a dual band Wi-Fi. Dual band means it supports both 5 gigahertz as well as 2.4 gigahertz, and you have an RF cable connecting over there at the lower end of the antenna. And this is basically fabricated on a planar surface. So that's why it's easy to pack it with the rest of the circuits in the handset. And there are other challenges too, because the handset, it depends on how the user holds it. He might hold it vertically. Most commonly it's vertical direction, but who knows? You could place it on a smartphone. You could place on a horizontal surface too, and use speakerphone. So there, of course, then you have to take care how you take care of the polarization in both directions, in vertical and horizontal. Well, moving on to the antenna tilt. Now, this is a technique used to enhance the performance of a base station antenna, where to enhance the signal strength in a given area, you could tilt the antenna, the element of the antenna in the downward direction, as you see in the picture, and with an angle called tilt angle. So this will reduce your path loss. It will reduce your delay spread. It will reduce your transmit power needed too, because you need less energy. You are not wasting RF energy outside where it's not needed, but you are focusing on the users where it is needed. And you reduce system interference, and you even reduce co-channel interference, because your signal is contained within a small area. It's not transmitted to other cells. And this helps you to increase your system capacity. You improve your signal to noise ratio and also improve network performance. Now, antenna tilt can be done in two ways. Well, there is a question, why not tilt the beam itself electrically? Yes, of course, that is possible. But in simple antennas, that cannot be done, because you need an array of antennas. If you have arrays are expensive, antenna arrays are expensive, and they are used only for specific single elements. You cannot tilt the beam. You have to physically tilt it. Okay. So static tilt. In static tilt, you preset during network deployment. When you install the cell tower and the antenna on top of it, then you determine what should be a tilt angle, and you mount it accordingly. Then, but there are now new variations coming, like remote electrical tilt, or RET. Now, this is dynamically controlled with a stepper motor attached to the antenna, and it allows to optimize tilt angle based on traffic load. In urban areas and even suburban areas, the traffic load can change from time to time. Like morning commute, there may be more load, and evening commute, if it's a highway, again, the load is very high. But at midnight, the load is very low. So remotely, the operator can just control the tilt angle to maximize the signal to noise ratio based on when the users are present and when the users are not present in the desired target area. So this is the most commonly preferred in the modern antenna installations. Okay, with that said, let's start with MIMO, multiple input and multiple output. Now, most of you must have, this is a buzzword in the 4G wireless telecom industry, but let's see what it is. So basically, MIMO is, you have multiple transmit as well as receive antennas. In previous webinars, we have seen that you can have an antenna array, a phased antenna array, which is basically on the transmitter on the base station, you could have multiple antennas, because it's very easy to install antennas on the transmit side or the base station side. But how about like if we have multiple antennas on the handset too, or on our wireless router, then there are multiple possibilities. And that is where MIMO comes in, multiple input and multiple output. What this means, you insert multiple data streams into the RF channel. That means you have multiple RF channels, and you take out multiple data streams from the RF channel. So multiple input from the transmitter side and multiple output when you take out data streams from the RF channel on the receive side. So that is how this term, somebody has coined this term, and it's very commonly understood now. Now, before we jump onto MIMO, let's have a little background. Where does it come from? Now, even we talk about MIMO, we had a SISO system, a single input and single output. In fact, most of the wireless communication that has happened so far in the history of wireless, it is SISO, single input, single output. You have a single RF channel which is carrying a single data stream from the transmitter to the receiver, or a single analog or digital signal from the transmitter to the receiver. This is called single input, single output. In fact, this is the most commonly used configuration in wireless communications. Now, if you see this picture, you must have seen these dish-like antennas installed on the sides of the cell towers. You know, on the top of the cell tower, you have the vertical rod antennas, but on the side, you will see these dish-like antennas. Now, these are microwave links. These are used for point-to-point connectivity, and these are single input, single output channels. This is a SISO system, actually, because you just have one RF channel and a single signal is transmitted from the transmit to receiver. Now, there's a question. Input means transmit and output means receive. Well, you could say that, but actually, if you take the RF channel as the reference, RF channel, what we are putting into RF channel and what we are taking out of the RF channel. The RF channel or the wireless channel is free space, actually, right? So from the transmitter side, we are inputting our data into the channel, and from the receiver side, we are taking the signal out of the RF channel. So it's very important to clarify this. The reference is not the device, but the reference is the RF channel. What we are putting into the channel and what we are taking out. If we are putting into it, that means on the transmitter side, we are inputting data or inputting signal, then it's input port, and the output port is when we are taking out the channel, out the signal from the channel. I hope I've clarified this. Okay. So now let's move on to the next one. After SISO, we have a SIMO system, a single input and multiple outputs. This is another, we take it to the next level, where we have multiple receive antennas, multiple antennas on the receive side and a single antenna on the transmit side. Now, this can be useful too. As we have seen in a previous webinar, that the radio signal travels in different paths. It could travel over different paths. So we could have multiple receive antennas deployed on the receiver to catch those signals. Now, there's a question here. With the SISO, we can have issue with rise to problems with multipath effects. Yeah, you are very, very correct. With SISO, that is why, see, this is a progression. So far in the history, historically, we had a SISO system. So we have problems with that due to multipath effects, due to fading, inter-symbol interference, all that stuff. That is why we are moving on to, we are making our antenna system better. So with the SIMO, we try to tackle this fading problem. We have multiple antennas on the receive side. We have a single input and multiple output system here. Okay, so this is how a demonstration of how a SIMO system will look like. You have 3 paths over here. The first signal is the line of sight signal from the cell tower. The second one is coming from the building. It's reflected from the building. And the third one is coming from a hilltop. So you could have a SIMO system where on the receive side, you have 3 antennas to capture all these 3 signals. And thus, if one signal fades, you have another signal available. Or if the second one fades, we have the first one available. Because all these 3 signals will not fade at the same time. They are independently fading. Okay. So let's move on to the next configuration. We have a MISO, multiple input and single output. Now here, on the receiver side or on the handset side, usually it is not possible to have more than one antenna. Of course, if you have a portable wireless router, as we saw in the previous picture, you could have 3 antennas or 4 antennas or whatever you have. But on your handset or smartphone, there is very little space. You have a single antenna. So there you use a MISO system. You have a multiple antennas on transmit side. On cell tower, you could have as many antennas you want, basically. Okay, you have more space and more carrying capacity over there. Now here too, this configuration too has benefits, because now you have 3 same data stream transmitted over 3 RF channels. If you lose one, you still have the second one available, or if you lose the second one, you still have the third one available, even on a single antenna. Plus, if all of them are available, you could transmit more data. You can multiply your throughput. Imagine like if you had a desktop PC connected with a single Ethernet cable to your local area network. And imagine if you connect 3 Ethernet cables with 3 network interface cards to your desktop PC, then you multiply your throughput by how much? 3 times. Now same principle applies here. You have 3 RF channels. You could multiply by your throughput by 3, because you have 3 transmitter antennas pumping in data to the receiver. Okay. Now this is just a picture of like multiple antennas on a cell tower and a handset receiving 3 radio signals from the cell tower. Okay. Now finally we have the MIMO configuration, where we have multiple antennas both on the transmit side and the receive side. Now there is a question here. What is the difference between having multiple antennas and an array system of antennas? Yes, array system of antennas also has multiple elements. So only difference between MIMO and array is in MIMO, you assume that the receiver also can have multiple antennas, not just the transmitter. When we just say phased array of antennas, it's only the base station or the antenna array. We don't care about the receiver. But here the receiver is part of the picture. We will design the system in such a way that if the receiver has more antennas, it can benefit from the MIMO, the properties of a MIMO system. So basically, yeah, the MIMO system is a superset of, you can say, multiple antennas or an array system of antennas. The definition is a little more enhanced in this case. Okay. Now, before we, let's pause for a while and let's just recall what we learned so far. So which antenna configuration is depicted by the following figure? Is it a SISO, a SIMO, or MISO, or MIMO? You can type your answer number in your text box, chat box. Okay, some people are answering. It's number 1. Very good. So this is a SISO system. You know, this is a typical television transmitter tower, which is transmitting, broadcasting one TV channel. Okay, and the receivers, they have a single input antenna. So at any point of time, basically, it's inputting only one information channel or a data channel or a video channel into the RF channel, RF communication system, and the receiver is taking out only one channel from the RF, one TV channel, information channel or video channel from the RF communication system and inputting to the antenna. Okay, very good. So all of you have answered it correctly. So let's move on to the next slide. So now let's see what all benefits we get out of MIMO. What are the promises of this MIMO system? Why do we have, what do we get out of it? You know, having multiple antennas on the receiver side definitely it's more complex to design, and it has its own challenges. It's not easy to put multiple antennas on a handset. So, but of course, the promises are you get a robust radio channel because you know you have multiple paths available, so you don't lose signal at all. Your effects of fading and multipath interference can be mitigated. There'll be no breaks in voice calls or data. You get higher throughput if the environment conditions are right. You get all the multiple channels simultaneously. You can increase your throughput. You'll have faster downloads, and with the demands placed by the latest applications on smartphones, this is the right solution. You get more megabits per second with the existing frequency spectrum and power, and it also enables this antenna configuration enables all the leading 4G wireless broadband applications. The wireless LAN standard, which is IEEE 802.11n and /AD advanced, or a WiMAX IEEE 802.16m or LTE advanced 3GPP release 10. So in cellular systems, the LTE is finding more application, and WiMAX does have application in some parts of the world, and wireless LAN, this is for home and enterprise and business use. Okay. So let's now move on to the next one. How do we actually realize these promises? By using antenna diversity, receive diversity or transmit diversity, by beamforming techniques, and by using space division multiplexing, SDM. Now what is this? We know about frequency division multiplexing, FDM or TDM. Now this is the new one, space division multiplexing, where we use space as a resource. Instead of using frequency or time as a resource, we use space as a resource. We can transmit multiple beams from multiple directions at the same frequency and utilize the fact that we have abundant space available around us. Now let's look at beamforming. Okay, there's a question here. In other sources, they describe 3 MIMO techniques: transmit beamforming, spatial multiplexing, and maximal ratio calculation. What is the difference in approach? Well, these 3 are interrelated, as we see in the slides. The transmit beamforming is the beamforming, actually, what we are saying here. Okay, so we form a beam from the transmitter side. Now, spatial multiplexing is one of the techniques that we'll see how we use it, how we use spatial multiplexing. And maximal ratio calculation is that we have seen this in a previous webinar. That is how we calculate the signal, the multiple signals from different RF beams. Maximal ratio. We give more weightage to the strongest signal and less weightage to the weakest signal. So these are only 3 different aspects of MIMO actually, which are required to implement a full MIMO system. So in beamforming, we control the shape and direction of the radio signals, in which direction we are transmitting them. So of course, if we have multiple antennas, then we can do this. Single antenna, we cannot steer the electrical beam, but with multiple antennas, we can steer our radio beam in wherever the users are. We can target our beam in that direction. Well, we can use it on both transmit or receive antenna arrays, extends range of radio signals in a direction, and signals from multiple antennas add up constructively to maximize receiver gain. And in addition, it also mitigates effects of multipath propagation, because now we are focusing our RF energy in one direction, one preferred direction. So that will mitigate multipath propagation, because we know in this path there are no obstacles. We will focus on that. Okay. So this is just a demonstration that the beam goes where the user population goes. So there's a question. So we can determine the best path the signal should take in order to reach a client device. Well, yes, that is true. So see, most preferred is always line of sight. But then line of sight may not work all the time. There could be obstacles on the way. So that is true. That based on the feedback received from the client device, we can adjust our signal strength, direction, and everything else. There are if we go in detail into the formats used in LTE and GSM and in other new the Wi-Fi new 4G wireless broadband standards, we'll see how that is done. But that is not covered in this webinar, the details of that. But definitely that is possible. Okay, but isn't the SLL an issue too in beamforming? Well, yes. These issues will be there actually, and we have to tackle that with appropriate consideration. Okay. So now let's move on to the space division multiplexing, SDM. So in this case, what we are doing, we are transmitting and receiving different signals simultaneously over the same RF bandwidth. We don't add more frequency spectrum, but using the same spectrum, we transmit beams in preferred directions. So in the picture you see M cross N MIMO system. You have M antennas on the transmitter side and N antennas on the receiver side, and you could have so many combinations. One transmitting to N and two transmitting to 1 and M transmitting to 2 and so on. So this exploits spatial separation between these RF beams to achieve higher throughput. And you know, one thing to remember, that it's ideal for RF channels with high signal to noise ratio. You know, if as you have seen, like the signal to noise ratio can vary for a RF channel. Now, if the environment conditions are right, you could basically have the maximum throughput. In whatever direction you transmit a beam, you will get a throughput. But if they are not ideal, if they are non-ideal, then of course your throughput will be reduced, because then you have to accommodate for other factors. Well, now here we see a signal path coefficients H11, H22, H21. These are assigned to each RF channel. These represent the amplitude and phase response for each signal path. You know, we with all these different RF signals coming from different directions, we need some mechanism to separate them actually. How do we know that this signal is coming from this antenna on that antenna? So the signature here is amplitude response and the phase response. That what is the amplitude response and phase response for this particular signal? That is how we identify. And those are represented with these values, mathematical values which you're seeing, H11, H21, H22, and so on. So for any MIMO system to operate properly, we must know these coefficients beforehand. Before any communication can begin from the transmit to receive side, we have to determine these coefficients. And that is why each of these standards, WiMAX and LTE, they have a training sequence. There is a training period when the handset comes up to power and tries to establish a connection with the transmitter. It will go through a training sequence. So training sequence is what? It will just determine the amplitude and phase response of each signal. How many different signals are received from the transmitter side, and how do we identify each signal separately? So the transmitter generates known training signal, which is known to the receiver in advance, and the receiver then processes the training signal to estimate path responses. Now, once we determine these signal coefficients in a MIMO system, this is how we represent this mathematically. There's a matrix formed out of it, H11, H21, and so on. And this represents the MIMO channel mathematical. This is a mathematical representation of a MIMO channel. Each of these values represent the amplitude and phase response. And this simple equation that the received matrix is what? It's a product of the MIMO channel matrix, the signal path coefficient matrix H, and the transmitted signal matrix T. and you derive the transmitted signal by doing an inverse of H and multiplying it with the received signals. So all this will be done by the digital signal processor inside your wireless equipment, inside the transmitter electronics or the receiver electronics. Okay. Now, before we move on, let's have another question here. So which technique will you recommend when the radio channel is very noisy? In other words, the signal to noise ratio is very low. So please type your answer. The first one is space division multiplexing. The second one is transmit antenna diversity. Number 3 is space-time block codes. Number 4 is time division multiplexing. Well, some answers are coming in. The correct answer is 2, transmit antenna diversity. Very right. The correct, I'm sorry. The correct answer is transmit antenna diversity. You know, as we said before, that if your signal to noise ratio is very high, then you can use all the RF channels. You don't care about it's noisy or not, because it's guaranteed. The bandwidth is guaranteed. The throughput is guaranteed. But if the SNR is low, then of course you have to transmit. You have to use more diversity on the transmit side. You have to transmit more redundant beams so that at least one of them will reach the receiver. Very good. So let's move on to the next one. Now there is one term we need to understand: multiplexing rate. What does it mean? So this is simply what it means is number of distinct data streams that can be received correctly and simultaneously by a MIMO system. So if it is M by N MIMO, it is the minimum of 2. Now you see in this configuration, the base station has 3 antennas, and the single user, it has 2 antennas. So what happens here? You cannot receive more than 2 distinct data streams because there are only 2 antennas on the receiver side, right? So it is a minimum of 2 which matters. Your throughput will be multiplied by 2. So how do you determine your multiplexing rate? Like if it is a 3 by 2 MIMO system, or let's say if it is a 5 by 4 MIMO system, what is the minimum number? Is 4. So there are 4 antennas on the receive side. That means your throughput cannot be more than a multiplier of 4. In this case, it is 2. You can double your throughput, but you can't make it 3 times because we only have 2 antennas. So it's the equivalent of, you know, the slowest link matters actually. In a network of multiple network elements, if you have more than, let's say, 10 network elements, the data travels through all these elements in the network. So the slowest one determines the total network bandwidth. Because if your server is very, very fast, but your client is very slow, still you can transmit only at the minimum of them, the minimum rate, the minimum of the server and the client. So it's the same thing here. You have only 2 antennas on the client side, so you can only have 2 distinct data streams. But there can be several different combinations. You could have a beam going from 1 to 1 and a 2 to 2, or you could have 1 to 1 and 3 to 2. Or you could have a combination 2, 2 and 3, 1. Or you could have 1, 2 or 3, 1. Again another one, 1, 2 and 2, 1. But it's never more than 2, 2, 1 and 3, 2. So next thing we need to understand is the diversity gain in MIMO. Now earlier we have talked about this diversity gain in previous webinar. Now here, for sake of simplicity, there is a simple way to estimate it. We assume that we have a narrowband system with slow fading, then simply a product of M and N. So if we have a 3 by 2 MIMO, diversity gain is 6. What this simply means that the signal to noise ratio is improved by a factor of 6. Why? Because we have 6 different ways of transmitting data from the base station to the user. And so we just have a multiplier of 3 and 2, that is 6. Now here we see we have now competing demands on the MIMO system. On one side we have multiplexing rate, that means we need higher throughput. We need to make our throughput as high as possible. On the other side we have a diversity gain problem too, because we also need to mitigate fading and multipath problem and ISI inter-symbol interference. So how do we do? Fortunately, trade-off is possible. Now how? Let's say case 1, we have a reliable mode, that our requirement of our application is that we need a very reliable communication. This could be useful for, let's say, emergency response systems or military communications, or where the data cannot be lost at all. We need a very reliable system. Then we could adjust our multiplexing rate to 2. What this means, we are dedicating 2 antennas on the base station and 2 on the receiver for transmitting data, so that we have a multiplexing rate of 2. We're doubling our throughput, but we want to keep a reasonable diversity gain too. The remaining antennas, we are left with 3 on the transmit side and 2 on the receive side. So diversity gain will be 6 in that case. This is a reliable mode. Now let's take another case where we have a high rate mode where it doesn't matter if I lose the signal, but my throughput must be high. Then we keep multiplexing rate 3. We dedicate 3 antennas on the transmit side and 3 on the receive side for throughput. So 3 will be the multiplexing rate. The throughput will be 3 times of a SISO system. And in this case, we have a price to pay. Our diversity gain will be reduced because we are left with only 2 antennas on the transmit and 1 for the backup. So the backup antennas make up our diversity gain. 2 cross 1 will be 2. So, but this way the trade-off is possible. Based on the application, what type of applications where we are deploying MIMO system, we can adjust our throughput and diversity gain. But there is a compromise. A compromise has to be done. Well, let's look at a little more how this MIMO system is used by Wi-Fi. So this is a 802.11n standard which has adopted MIMO. It allows diversity up to 4x4. There is transmit beam forming possible. You have space division multiplexing, and you have 2 bands, as some of you might be knowing already, 2.4 and 5 gigahertz ISM band, and the bandwidth is 20 to 40 megahertz. Physical data rates can reach up to 600 megabits per second, whereas throughput is much more than 200 megabits per second. And it also extends the range because with MIMO system you have more range now. Indoor is 70 meters and outdoor is 250 meters. With a single MIMO system, you could actually cover more area. You will need less wireless and repeaters, but a single MIMO system can cover maybe whole of the enterprise campus. Well, now let's consider the what type of antennas are used for access points in a MIMO system. So here you see a narrowband monopole system. You have 3 antennas you see on the wireless router, and each of them is a quarter wave monopole separated by half wavelength. Well, there's a question: why a problem with TV frequency in UK? Okay, this seems to be a specific problem in UK. Why a problem with TV frequency in UK? Okay, for LTE. Well, so these type of problems happen when the LTE, although the LTE frequency allocation is based on a countrywide, right? So when we go to LTE slide, I'll show you what frequency band is available basically in different countries. So sometimes they might overlap. If it is very adjacent to a TV allocation in that country, it might interfere. So then it's for the regulatory body to decide how to keep the separation actually, because as we have discussed earlier too, the frequency spectrum is very congested. It's allocated to all these different users. We have TV frequencies assigned to TV channels. We have frequencies assigned to LTE, and even GSM is also in operation. Then you have wireless LAN. So, but you have to keep enough separation between all of these. This is the task of regulatory bodies actually. So definitely you have to keep a separation. Then the problem will be gone. I'm not very aware about what's the specific problem in the UK, but of course we can do online research and find out what's the problem, why they have assigned a TV frequency which is very close to the LTE frequency. So it's more of an operational problem, not a technical problem. Okay. All right. So next, let's look at what other antenna variations are possible in Wi-Fi. So antennas for access point, multi-band compact. This is another variation which makes it compact. You have a PIFA type of element, a planar inverted F type of antenna, where you see a 5 gigahertz element on the left side and 2.4 gigahertz on the right side. This is again fabricated on a planar surface. And in the top view of this router, you see 3 antennas installed at 120 each. And this type of configuration provides a very compact multi-band configuration for an access point. You won't even see the antennas coming out of the router. They are all inside with this type of configuration. Okay. Let's go to the next one, antennas for portable devices. Well, for portable devices, as we have seen before, there are trade-offs between design, performance, and placement. All these devices are packed with so much of stuff that you really have to be very creative. How you fabricate antenna for a portable device. So this is one configuration, case 1, where you have two antennas in the MIMO configuration, and they are on 2 different sides of the ground plane. Now here, of course, you have 2 different antenna feed points which are far apart. That will pose another problem. You need to have 2 feed points and to have to match their impedance. And in second case, you sacrifice some of diversity by having antennas side by side of each other on one side of the ground plane. But the benefit is you have antenna feed points much closer. So all the electronics, the impedance matching circuitry can lie on one side. So again, it depends on application to application, from handset to handset. It depends on, but these are different variations which are possible with these type of configurations. And the same holds true for cellular type of antennas too. So there's another question here. What is the recommended physical separation between antenna elements of a MIMO system? Is it quarter wavelength? Depends on the wireless standard. Is it minimum half wavelength or does not matter? Well, very good. This must be a simple question for you guys who have attended all the previous webinars. So it has to be half wavelength. We have seen that if we reduce it less than half wavelength, what happens? It becomes a reactive system. It doesn't no longer remains an antenna system. It becomes a reactive system. A reactive system which could be inductive or capacitive, and it becomes more like a transformer then. You know, a transformer is a reactive device where you have a primary winding and a secondary winding, and electromagnetic induction happens between the two windings. So if the separation between any two antennas in a MIMO system is less than half wavelength, the same thing will happen, and we'll lose the benefits of this RF performance that we have been discussing. Okay, now MIMO and WiMAX. Now WiMAX standard, it's still in operation in many countries. It has a predecessor of LTE actually, but it coexists with LTE too. So even the latest version of WiMAX also has full-featured MIMO, which supports antenna diversity, beamforming, space division multiplexing. And of course, there is a range here, 2.3 to 2.4, 3.3 to 3.4 gigahertz, which is country-specific range. It depends on the country where you are operating this. But you see, as somebody asked previously a question, that there is an interference with the TV channel in UK for LTE frequencies. Now here you see, if you allocate 2.4 gigahertz to WiMAX, then it overlaps with the Wi-Fi signals. So WiMAX signal will interfere with my wireless LAN signals too. So it all depends on how we keep separation between different frequencies which are allocated in a specific geographical region. It provides you 5 to 10 megahertz bandwidth, enhanced throughput because of MIMO, 1 gigabit per second for fixed stations and 100 megabit per second for mobile stations. Now the WiMAX adopts a new concept called a single user MIMO or a multi-user MIMO. Okay, there's a question here. Can you implement MIMO on ultra wideband antennas, and how do you decide the half wavelength in that case? Well, yes, it is possible conceptually. Okay, let's move on to when we discuss about feature of MIMO, we discuss a similar scenario over there. Of course, again, it's a wavelength that is a deciding factor here too. Half wavelength is written in stone. Like you have to keep it at least half wavelength, the separation between the two. Okay. Now we have we were talking about single or multi-user MIMO. A single user MIMO and a multi-user MIMO. Like we'll discuss this in a little more detail what it means. But this is how the commercial carriers have adopted MIMO in the current 4G wireless installations. Okay, MIMO in LTE advanced. Well, it's a release 10, 3GPP release 10. It has full-featured MIMO. Again, all those features are supported: antenna diversity, beamforming, space division multiplexing, STM. Frequency bands, there are 22 frequency bands now. So in UK, you will have one of these. It's a very wide range available, 698 to 3600 megahertz. So it depends on which frequency you're operating in. It depends on the allocation of frequency band within the broader frequency range. It has a scalable bandwidth, which is between 20 to 100 megahertz, enhanced throughput. Again, it also adopts the concept of single user MIMO and multi-user MIMO. Now let's see what is the meaning of the single user MIMO. In single user MIMO, single user gets the benefit of full throughput. So I'm assuming my receiver has capability to have multiple antennas. Like it may not be a smartphone or handset, it could be a wireless router, which could have more than one antenna, and it just gets the full benefit, all the full throughput, all the good benefits, all the excellent benefits of MIMO are utilized by a single user. There's no other use, just one single user. Now this could be more like a dedicated type of implementation for specific users, like by government, by military, by emergency response teams. They might use very high bandwidth and a MIMO system when they are on the field. So this is very ideal for that type of application. But most of the commercial carriers, like people like you and me, we may not need that high bandwidth. We have a single smartphone or a mobile phone which I am using daily, and I just want a guaranteed guaranteed minimum throughput that I need to do my task. In this case, most of the commercial carriers, they implement multi-user MIMO. This is what is called multi-user MIMO, where the base station does have multiple transmit antenna diversity, but on user side you have only single antenna. but you have the luxury of having multiple radio beams. You have multiple access to multiple radio beams carrying the same signal. So you don't have fading, you don't have inter-symbol interference. You get all the benefits of MIMO. So throughput, yeah, throughput your throughput will be limited, but still enough to cover your task. For a small device, you have enough bandwidth to download your videos and other stuff. But you are sharing the full bandwidth with other users, multiple users. In both LTE and WiMAX, multi-user MIMO is a configuration that is used because you have a range of subcarriers and each user will be assigned a specific subcarrier to use when transmitting, when receiving as well as transmitting. Okay. Now we come to a glimpse of the future. Massive MIMO and WiGig. There is a new standard from IEEE 822.11 AD. It is also called millimeter wave standard, and it's in the 60 gigahertz unlicensed band, where they define 4 channels of 2 gigahertz each. Now this is very high frequency, but what is the benefit? You get the benefit of small wavelength. Your wavelength is in the range of millimeters, 5 millimeters. If you have 60 gigahertz, your lambda is how much? 5 millimeters. That means you can have very small antennas. Your antenna, you see in this picture, in 1 centimeter square space, you are having how many elements? 16 elements. And the separation between each 2 elements is only 2.5 mm. Half wavelength is only 2.5 mm. So it is possible to fabricate arrays of antennas within a very small form factor. Now this gives us a lot of hope. The future smartphones and future handsets could utilize multiple antennas within a small form factor, and you could have a fully deployed MIMO system even on the receiver side, even on the side of handset. Of course, at this time you don't have any commercial handsets available like that, but this is where we are heading to with MIMO technology. With this, what you get not only on the handset side but on the base station side, you see in this typical example you are having 256 elements within the size of a pizza box. I think all of you must have had a pizza box. As you've seen a pizza box, what is the size? It's a handheld size. Within that size you have 256 antenna elements with this high frequency. So this collectively, this approach collectively we call it massive MIMO. It's a very intensive research area at this time, but definitely we are going to get some commercial applications of this in the coming years. Using massive MIMO, we will have MIMO implemented almost everywhere. Of course, you have to find a use case. Like if a user does not need a MIMO element, then who cares? If just one antenna in multi-user MIMO configurations is okay for me, then I'm fine. But there may be applications where the receiving side needs much more bandwidth in a small form factor. Could be enterprise applications or could be small business applications. So there is a question here. What is the gain seen? Could you repeat your question? What is the gain seen? You mean the antenna gain? Well, here, if we want to calculate the antenna gain, but that is what you're asking, then we'll in the previous webinar we talked about that, how we calculate gain for an array actually. So how many transmit receive circuits we have in this case? Well, each antenna will have its own independent feed. It's how you configure it actually. In antenna engineering part 1 of 2, we have considered this problem in little detail with the phased array antennas, where we have Butler networks and other networks feeding signals to each of these elements. But of course, here that's a challenge. Here you don't have 8 elements as we have in the previous case. Now we have 256 elements. So the gain will not be small. Yes, gain will not be small. So the benefit here is that you could have multiple independent beams, just like in a phased array, or you could have a single beam that you can reach out to a great length, a great distance. What type of application you want to have? You could have sub-arrays formed out of these 256 elements. You could have sub-arrays. I could have, like, say, 8 sub-arrays and 8 independent beams, or I could have 4 independent beams, or I could have a single beam. So this basically, all these, what we are doing here is the phased array, which is a very mature technology, which is used in space, astronomy, and radar communication, and radar detection, and military communications. We are bringing that technology onto the consumer electronics. Now we have base stations having all that phased array structure available, and so only future will tell, but all interesting applications will come out of it. But this is where it is heading to. you get a phased array in the size of a pizza box with multiple independent elements. Now, of course, here the frequency is 60 gigahertz. Currently, there are some applications where we use this high frequency for wireless backhaul. Wireless backhaul means when you connect a base station antenna to the core network, you use high frequency because you need more bandwidth. You have to carry so much of data from different users which are connected on the wireless network that you need a high frequency to carry all that bandwidth. 60 gigahertz, and there is another higher band available, 80 gigahertz. So 60 and 80 gigahertz are the bands available for high bandwidth wireless communication. It's mostly a point-to-point communication in that case. Of course, there'll be other challenges too. With this high frequency, it cannot go very far. It will be a short distance communication, right? Because higher the frequency, the more are the losses. The propagation losses increase as you increase frequency. Okay, so very good. I think we are heading to the end of this webinar. Now, this is a list of research papers and books that I have put in here in this slide. All of you will get a copy of the slide. I'll email you the copy of the slide so that you can use if you want to dig deeper into any of these research areas, and there are books, list of books and research papers that you can use. Okay, now, so copy of the slides from this webinar will be emailed to you. And there is how do you claim a professional development hour and a certificate of completion. So after this webinar ends, you will be redirected to a webinar forum page at this link, where I expect you to complete a feedback form and respond to a problem statement from this webinar. So once you complete the response to that statement, I will email you the certificate of completion, which you can use wherever you want to present it, that you attended 1 hour and you developed yourself professionally in this area. My contact information is given here. I am open to receiving emails, answering questions about anything about this webinar. Plus, you are welcome to visit our website, uspertech.com, where you can learn about other webinars, upcoming webinars, recorded versions of previous webinars. If you missed any of the webinars, you can always go to the recording and watch it. If you have any technical problems, let me know. I'll resolve those. And we also have on-site training service. If any one of you in your organization, if you are expecting that one of our instructors visits you and holds a customized seminar or training for a group of people, then we are open to that too. Please help us know about that if you want those type of services. And any other questions you may have, I'll keep 1 minute or so for that. Well, next webinar at this time, my date is not final. I'll definitely send out invite to you, all you guys, invite you to the next webinar. And I hope you enjoyed this webinar. If I am open to any suggestions, questions to improve the quality of this webinar. Okay, there's a question. Site survey topic. Well, site survey we touched it last Saturday in Antenna Engineering Part 2A of 2. The recording of that is available. I think there are a couple of slides over there on site survey. Okay, very good. So thank you very much for attending this webinar. I'm going to close it now. And after this meeting ends, just wait for a web page to come up on your screen where you can complete the requirements for your certificate of completion. Thank you very much.